Hello, welcome to the lecture 6 of the course Transportation Network Analysis. So, in the last lecture we were discussing the scheduling problem and we had started to discuss some of the constraints that are required in this problem. So, if you remember, we had this variable delta ik that we had introduced. So, that was defined to be equal to 1 if a job ji is started before job jk on the same processor and 0 otherwise. So, the reason to introduce that was to ensure that if two tasks are being executed on the same processor and it is given that one of the tasks has starting time of the other processor, then the first task should complete before we can start the other task. Okay. So, let us now represent that constraint here. So, the constraint is like this: Si plus tau I minus Sk less than or equal to capital T times 1 minus delta Ik plus 2 minus Pij minus Pkj, and this holds for every processor j and for every pair of tasks I and k such that the tasks I and k are not the same tasks. So, let us look what is this constraint doing here. So, if delta Ik is equal to 1, it is given that the starting time of task ji is less than the starting time of task jk, and it is also given that Pij and Pkj are both equal to 1, that is the tasks ji and jk are both being implemented on the processor j. So, then we want that this task ji executes before we start the task jk. Okay. So, let us look here. So, if delta Ik is equal to 1, Pij is also equal to 1 and Pkj is also equal to 1. So, in the RHS we will have 0, capital T times 0, okay, and that is equal to 0. So, finally, we will be having this condition that Si plus tau I minus Sk is less than or equal to 0, okay, and that is what we wanted, that the starting time of the task ji plus the time to execute this task tau I is less than or equal to the starting time of task jk, okay. And this condition is only restrictive when delta Ik is also equal to 1, Pij is also equal to 1 and Pkj is also equal to 1. If that is not the case, if any one of these variables is not equal to 1, then what will happen is that this term in the bracket in the RHS, this will not be 0, but some integer value greater than 0. So, then this whole RHS which is having this capital T times this term in the bracket, that will be something positive, okay. So, then this will not have any effect, or this will not be important to the condition that we want here. And just to remind you again why capital T is getting multiplied here, because it can happen that this difference Si plus tau I minus Sk can be something greater than 1 also, okay. And in that case we have this capital T on the right hand side, so that there is an upper bound on this Si plus tau I minus Sk that is specified, okay. So, we have been using this variable capital T a lot of times in this scheduling problem, because that is the time it takes to process all of the tasks if they are processed on a single processor, okay. So, we can never have, for example, the difference of the two starting times of two tasks to be greater than this. So, this is kind of a limit, okay. This is the total time it will take if you process all of these tasks on a single processor. So, that is why you will be seeing this capital T getting multiplied at many places in the constraints in this scheduling problem, okay. Now, in the previous constraint that we saw, it was given that although there are two tasks that are being implemented on the same processor, but the starting time of one of the tasks was less than the starting time of the other task, okay, that condition was also given. One thing which we also need to rule out here is that if two tasks j and jk are executed on the same processor j, that is Pij is also equal to 1 and Pkj is also equal to 1, and therefore their sum Pij plus Pkj will be equal to 2, then these tasks ji and jk cannot have the same starting times, okay. So, what it means is that then either one of these tasks should have starting time less than the starting time of the other task, okay. So, mathematically that will be the case that either delta Ik is equal to 1 or delta Ki equal to 1. Note that we cannot have that condition that both delta Ik and delta Ki are equal to 1, because what does it mean if delta Ik is equal to 1? It means that Si is less than Sk. And what does it mean if delta Ki is equal to 1? It means Sk is less than Si, and both of these two conditions cannot hold simultaneously. So, we cannot have delta Ik and delta Ki to be equal to 1 simultaneously. Okay, so let us see how we can represent this constraint here that I mentioned mathematically. So, this is the way we represent that constraint here. So, we will be writing Pij plus Pkj minus 1 is less than or equal to delta Ik plus delta Ki, okay, and this holds for every processor j and for every pair of tasks ji and jk, such that the tasks are not the same here. That is what it means, I not equal to k here. So, you can see that when Pij and Pkj are both equal to 1 here, so the LHS is equal to 2 minus 1, which is equal to 1, and if the LHS is equal to 1, then either delta Ik or delta Ki has to be equal to 1, okay. So, that is how this constraint gets represented mathematically, and this constraint is only restrictive when Pij plus Pkj is equal to 2, that is both Pij and Pkj are equal to 1, and only in that case this constraint will be restrictive, because if suppose either one of these is not equal to 1 or both of them are equal to 0, so in that case this quantity on the left hand side will be something less than or equal to 0, and then it does not put any constraint on the values that delta Ik or delta Ki should take. So, since delta Ik and delta Ki anyway are integer variables, so then whether they take the value 0 or 1, this condition will always be satisfied, that 0 is less than or equal to delta Ik plus delta Ki. So, this constraint is only restrictive when both Pij and Pkj are equal to 1, okay, and therefore the sum of these two variables is equal to 2. Okay, let us discuss another constraint here. If you remember, I had specified this set capital E. So, this set capital E is representing precedence relations between different tasks, okay. So, if there is an edge that starts from task ji and ends in task jk, then there is a condition that is given that task jk should only start when task ji is completely executed, okay, and this condition should hold regardless of the processor on which you are executing this, okay. So, whichever processor you decide to execute these two tasks ji and jk, you have to ensure that jk only starts getting executed after we have executed the task ji, okay. So, this can be represented mathematically by this constraint here, that Si plus tau I minus Sk is less than or equal to 0 whenever there is an edge that starts from task ji and ends in task jk, okay. So, this is what it is meaning. So, it is saying that the starting time of the task ji plus the time it takes to execute the task ji should be less than or equal to the starting time of task jk, okay. Now, we also had mentioned that there can be some deadlines for every task. So, di here, if you recall, is the time by which task ji should be completed. So, mathematically it means that the starting time of task ji plus the time it takes to execute the task, that is tau I, should be less than or equal to di, and that should hold for every task ji here, okay. And finally, we also require that we need to define this finishing time f here. So, if you remember, finishing time f is that time at which the last task gets executed among all of the tasks that we have, okay. So, if that is the case, then the finishing time f should be then greater than equal to the starting plus the time it takes to execute a particular job ji, and this should hold for every task ji or the job ji, okay. So, the finishing time will always be greater than equal to Si plus tau I for every task tau I here, okay. And you can see here that although f is greater than equal to Si plus tau I, but since the objective function is to minimize f here, So, f wants to be as small as possible, but then there are these lower bounds on how much small the f can be. Okay. So, therefore, this in the optimal solution f will be equal to the starting plus the time it takes to execute the last task in on any of the processors. Okay. And for all the other tasks that are getting executed before this last task, for them this f will be greater than their starting plus the execution times. Okay. So, with this we have discussed the scheduling problem. So, we discussed a lot of these combinatorial optimization problems, starting from knapsack problem, we had this coverage problem, traveling salesman problem, scheduling problem, and so on. So, all of these optimization problems are kind of integer programs, as we had seen, because some of the Decian variables were restricted to be integers. If you recall, this is the optimization formulation for the shortest path problem. This we had seen before, and here the objective is to minimize the total system travel time for a path that starts from origin node R and ends in destination node S. These were the set of constraints that were ensuring path connectivity. So that we get a path that starts from the origin node R and ends in the destination node S, and then we have these definitional constraints here that the XA variables have to take binary values only. So, this integer program is kind of integer linear program, okay, because the objective function and the constraints are linear in terms of the Decian variables. Okay. So, here you can see that this is not a pure linear program. So, we had seen examples of pure linear program. For example, let me give you example of pure linear programs. For example, if we have something like minimize x plus y, where both x and y are Decian variables. So, I will write x comma y in the bottom here, subject to suppose x greater than equal to 0, y greater than equal to 0, and say x plus y less than or equal to 2. Okay. So, this optimization formulation is an example of a linear program. In a way, you can think of a pure linear program, because these variables x and y are allowed to take continuous values subject to these constraints that are there. Okay. But the optimization formulation of the knapsack problem, there the Decian variables were restricted to only take integer values. Okay. So, they were all integer programs, they were not having these variables that can take continuous values. But there was one thing that, for example, this shortest path problem is an integer linear program, because the objective function first is a linear function with respect to the Decian variables that we have, because what is the objective function here? It is just minimizing the summation of Ta xa, where the summation goes through all of the edges here. So, that is a linear function, this summation Ta xa, this is a linear function, because Ta is a constant and xa are the Decian variables. Okay. Similarly, if you look at the constraints of the shortest path problem, they are also linear inequalities or equalities. Okay. So, that is why this is an integer linear program, but we cannot say that it is a linear program. Okay. And this shortest path problem formulation is also pure integer program, because all the Decian variables are integers. So, then you can think that there will be some other name for integer programs where we can also have some variables that can take continuous values. So, those integer programs where some of the variables are allowed to take continuous values are called mixed integer programs. Okay. Also, this shortest path problem is a binary integer program, because the Decian variable xa can only take two values, either it takes value 0 or value 1. Okay. Okay. So, why we are again revisiting these things? Because now we want to see one algorithm so that we can solve these different integer programs. So, the reason for discussing this algorithm is that it will offer a lot of insights into the how the optimization works and so on. And this algorithm is very special in the sense that although it is targeted to solve integer programs, but then we will be actually be just solving linear programs. So, let us move ahead in discussing in that direction. So, just to start, the motivation of why we need a different approach to solve integer programs and why we cannot use the approach that we have already seen for solving the linear programs. Let us look at this linear program here. It is trying to maximize x plus y subject to these constraints that 3x plus 8y is less than or equal to 24, 3x minus 4y is less than or equal to 6, okay, subject to x and y greater than or equal to 0. So, this is that feasible region that we have here, okay. So, this feasible region is given by yellow here. Now, it may not be very difficult for you to see that where the optimal solution will lie here. So, as we had seen that the optimal solution for a linear program will be there at one of the extreme points. So, if you maybe plot the contours of this function x plus y here, it will go like this. So, it will increase as you will go in this direction. So, it will increase in this direction x plus y. So, these different lines will have different objective function values, and you can think that the maximum value will occur at this vertex here, okay. And therefore, the optimal solution for this linear program is this point here, which is given by 4 comma 3 by 2, okay. So, since this was a simple linear program, so we could just look at one of these extreme points or the corner points, and then we determine the optimal solution. Okay. Now, let us make a change here, that we are now restricting the variable x to only take integer values, but non-negative integer values, okay. But everything else stays the same. Now, you can see that the feasible region is given by these lines here, you see, okay, these orange colored lines here, and then there is this one single point here. Now, you can try to guess what will be the optimal solution now. Now, you can see that the feasible region for this optimization program is a subset of what was the feasible region for the corresponding linear program that we saw in the previous slide. So, one thing is clear that the best solution value that you can get from here can only be equal or less than the best value that you obtained from the last linear program, okay. And since it so happens that this point is still a feasible point for this optimization problem here, so the optimal solution is still this 4 comma 3 by 2, okay. And this is the case where the integrality did not matter in finding the optimal solution. So, even though we made one of the variables x to just take integer values, the optimal solution still remained the same here as was the case when all the decision variables were allowed to be continuous. Okay. Now, let us make one more change here. Now, we are restricting both x and y to take only non-negative integer values, okay. So, the feasible region now is a set of these points here, you can see, okay. And now, you can see that this point 4 comma 3 by 2 is no longer a feasible solution to this new optimization problem, okay, because 3 by 2 is a fractional value and therefore, it does not satisfy the condition that x and y are both integers. And the optimal solution in this case is one of these solutions is x and y take the values 2 and the other one is this 3 comma 1 here. In both the cases, the objective function value will be equal to 4, because 2 plus 2 is also equal to 4 and 3 plus 1 is also equal to 4 here. So, now this is interesting here, that the rounding of this solution 4 comma 3 by 2 that was obtained from the corresponding linear program, I mean. So, this rounding will not even give us the optimal or the even the feasible solution. Why is that? Because if you round this solution, then you will get either 4 comma 2 or 4 comma 1, okay, and it just so happens that both of these solutions are infeasible for the optimization problem that is shown in the last slides, okay. So, there are two things to be noted. First is that the solution this 4 comma 3 by 2, which was optimal for this linear program, and when we restricted both x and y to be integers, now this is not even a feasible solution, leave alone it being optimal, okay. And that is clear, because 3 by 2 is a fraction value. So, how it can be a feasible solution if we are restricting both x and y to be integers. And there is one more thing, that we cannot just use this solution 4 comma 3 by 2 and just round it to the nearest integers, hoping that we will be getting the optimal solution for this new optimization problem where we have restricted x and y to integers, because even when we do that, we get these solutions 4 comma 2 and 4 comma 1 here, which are also not feasible. So, this kind of trick will not work, that you solve the corresponding linear program of an integer program and maybe just try to round the solutions for the optimization problem that you obtained by solving the corresponding linear program, okay. So, that kind of trick will also not work. So, therefore, we need different techniques for solving integer programs altogether, and we cannot use the algorithms that we know for solving linear programs, okay. So, this was the motivation to develop new approaches for solving integer programs as compared to the approach for solving the linear program. So, for the linear program, we had this property that the optimal solution lies at one of the extreme points, but that does not work here, okay. So, in the next class, we will be discussing this algorithms branch and bound. So, there we will be seeing how we can solve various integer programs. Thank you.